let's introduce you to the idea of the intermediate value theorem. The intermediate value theorem is used quite a bit. Typically, it's used in proofs. It's used in other proofs. It's not all that often used directly to solve something, but it was very commonly used in other proofs. So it's a good idea to have some feeling for what this thing is. So let's start off with the idea: if f is continuous on this closed interval a to b, and k is any value between f of a and f of b, then there is at least one value c in ab such that f of c equals k. Okay, that's a mouthful. Let's see if I can draw this and make a little sense out of it. So I'm going to have this closed interval a to b, and I know my function f is continuous on this interval, so I'm just going to draw some function f like that, make it continuous. So this value right here would be f of a. I need to move my y a little bit. This value right here would be f of b. This is the y-axis. So what this is saying is that k is any value between a and b, f of a and f of b. So over here someplace, let's pick another color. Some value k is clearly between f of a and f of b on the y-axis. Then there's at least one value. There could be a bunch. There could be an infinite number of values. Depends what function we're looking at. But you're guaranteed there's at least one value c in a to b. So there's going to be a c somewhere down here such that f of c equals k. And the way this is drawn, yeah, it's right there. So this right here is in fact f of c, which is equal to k. That's all the intermediate value theorem says. It may sound like kind of an odd theorem, but really this can be a little bit intricate to actually try to prove this is true. So anyway, this is what this is saying. If the function is continuous on the closed interval, if I pick any value between f of a and f of b, there's at least one c in the domain here of one x value such that f of that x, f of c, is equal to k. Now the intermediate value theorem is actually known as an existence theorem. It proves the existence of a value but tells you nothing about how you're going to actually find it. And like I said earlier, this is most commonly used to prove other theorems. So let's use the intermediate value theorem to prove there's at least one zero of the function x squared plus x minus 6 on the interval 1 to 3. Okay, well, this is what I'm thinking of by my definition as a, and this is what I'm thinking of as my definition of b. Now, this is a polynomial. Therefore, it's continuous everywhere. So if it's continuous everywhere, clearly it's continuous on this closed interval. So now I need to find f of a. Well, f of a equals f of 1, which is 1 squared plus 1 minus 6. That's a negative 4. And what is f of b? Well, f of b is 3. So that's f of 3. That's 3 squared plus 3 minus 6. That's 9 plus 3. That's 12 minus 6. That is 6. So, is there a 0? Well, yeah, this is continuous. F of a is a negative 4. F of b is a 6. 0, just plot the number line here. Negative 4, 3, 2, 1. Here's 0. 1, 2, 3, 4, 5, 6. So, yeah, 0's between 4 and 6. So, there is some value, c, if I were to, let me see, I'm going to change this to an x and y axes. On the y-axis, I'm down here at negative 4. I'm up here at 6. 0 is between negative 4 and 6. So I don't know what this function looks like. Actually, I kind of do. It's a quadratic. It's not going to be too hard to figure out. But I've been guaranteed that there's at least one value. There's a c somewhere between 1 and 3. Somewhere between 1 and 3, there's some value c such that f of c is going to be equal to 0. So in other words, somewhere in here, this function is going to cross the x-axis somewhere.